Okay, so now that we've covered some of the basic I2C commands, now we need to go ahead and find the pins on our microcontroller that can actually do I2C. So if you go to the platforms page and click Freedom KL25Z, it'll actually take you to this web page that'll actually list out all the different pins and their different uses. So this is a very, very helpful little picture right here, and it actually shows us a few I2C lines. So as you can see right here, PTC9 and PTC8 can act as an I2C line, where PTC9 works as the data line, and PTC8 works as the clock line. And as you can see, there's a variety as well. So the idea behind this, though, is that you can see that there's I2C0 and there's I2C1. The reason for that is the KL25Z can run two I2C lines at the same time. So you can actually, instead of having like one I2C line with 100 different slaves, you can actually have two of them, each of them having 50 slaves. It just helps to make it so that the coding is a little bit more streamlined, and it keeps things maybe a little bit more organized. But the way that it ultimately works is that you can at most have I2C0 and I2C1 running at the same time. You cannot have two pins, each of them mapped to I2C1, running two I2C lines, because that just won't work. So in the case with this one, you can't use PTC11 and PTC10 as an I2C line, and PTC2 and PTC1 as another I2C line, because they're both mapped to I2C1. So this is just another thing to keep in mind, is that this is just a listing of some of the I2C pins. But in fact, there are actually a lot more, and you can actually map them to different types of pins if you want to. So the way that you can find out about this is if you go to the mBed source code for the library mBed.h, the one that we've always been importing in all of our programs, and you go to mBed source. So you can type that into the search bar right here, and it'll actually take you to it. And then you click on a folder called targets, and you click on another folder called HAL, and you click another folder called target_freescale, and click on target_klxx, then target_kl25z, and then go to this one file called peripheralpins.c. You'll actually be sent to this little source code that lists out all the different pins and their respective uses. So as you can see right here, you can actually see like these are all the pins you can use for the analog to digital converters that we talked about previously. And this is the one pin that we can use for the digital to analog converter. So PTE30 can be used as a digital to analog converter. And right here is the I2C pins that you can use. So as you can see, these are all of the I2C data line pins, and these are all the I2C clock pins. So as you can see right here, you can in fact use PT25, which is mapped to the I2C0 line, and use PT24 as the clock. So you can use PT25 as a data line and PT24 as a clock. Now this is kind of a theoretical thing, because unfortunately, if you scroll down to this image, you'll see that PT24 and PT25 are already used on board on this microcontroller, which are used to access the accelerometer on this board. So there is already an onboard accelerometer on this board. We're not going to be utilizing that one, but there is plenty of source code available if you want to go ahead and use this accelerometer. And so with that, again, you can variety and mix and mash as you need to. So you don't have to say PTC9 and PTC8. You can also say PTC9, and you can also therefore say PTE24, because they're both mapped to the I2C0 lines. And this is kind of a mix and match thing. Go ahead and test as many I2C pins as you want. So there's a little problem here that there might be a few bugs depending on which pins you use. So I've played around with a fair bit myself. And so far, the one that I like to use is the PTB1 line as my data line, and PTB0 as my clock line, because it seemed to be, for me in my instance, one of the more reliable I2C pin lines. So we're going to be using that for our code demonstration. Before we even get started with writing up the code up, we're going to go ahead and look at how to actually communicate with this. So there's a library already for I2C. So if you go to on the web page, you go to Handbook, and then go to scroll down to communication interfaces. There's I2C. So this is the API, or the library code that you can use to interface with I2C devices. So you scroll down, here is the list of all the functions that you'll need. So I2C, this one creates the class. So you input the serial data pin and the serial clock pin into this, and you can create the I2C class. You can set the frequency of the clock speed of it. So in the case with us, our maximum clock speed for the color sensor is 400 kilohertz. So we're going to set this to 200 kilohertz in our code. Next are these read and write functions and the start and stop. So start and stop is create the the start condition or the start signal and the stop signal I2C that we previously discussed when discussing the protocol. Read and write. So there's two of them. We're going to use the more intense version, which has more input arguments than this one, because this is a lot more extensive and it makes it so that writing to these things is a lot easier. Write, pretty much you input the slave address of your device, then you put in whatever data you want to write after that. So in this case, it'll be like the command code or the register address, and then the actual data that you actually want to write to that address. Length just defines exactly how many bytes you want to send on top of the address. So in our case, because we're going to be sending the register address and then the data bytes, we're going to be sending out 2 bytes of data. The last one is Boolean repeated. So this one defines whether or not you want to create a repeated start condition or not. So this is more important if you want to actually read from the registers. So if you want to read from the registers, you set this to true to create the repeated start condition. Okay, so read is pretty much the exact same thing as write. So what you pretty much do is you input the slave address, and then you put whatever you want to write to the device, or actually what you actually want to get read back from it. So this is just a little character array that helps to store whatever gets read in. The length just determines exactly how many bytes you want to read back in, and this one, of course, defines whether or not you want to create a repeated start condition or not. So we're going to be using just frequency, this read, and this write command to actually communicate with the color sensor. Okay, so what I have here is the TCS34725. Again, this is the color sensor, and as you can see, the sensor is actually in the very center, so it's a pretty small sensor. It's smaller than my fingernail. And instead of actually getting this sensor and soldering onto a board, what I in fact decided to do was actually buy this from Adafruit Industries. So Adafruit Industries provides this little circuit board that puts the sensor on it, and it has a few other perks as well. So on this also has the pull-up resistors that you need for the I2C lines. So that's another additional perk, so I don't have to actually get resistors. So you'll notice that when we actually set this up, we don't use any pull-up resistors whatsoever. We just connect this straight up via wires, because the pull-up resistors, again, are already on this. So another perk about this as well is that there's actually a light sensor right here. There's actually an LED right here. So part of the LED, let me go ahead and just grab something just to give you an example. The idea behind the LED is that it helps to illuminate whatever object you want to actually detect the color of. So there's actually this general problem where, say, if you put, I have a rubber glove. If I put it over the sensor, what's going to happen is it's actually going to shadow the sensor, so you're not going to actually get the purple color that you would get for this glove. You would in fact just get like black or some grayish color, or something like that. So the LED helps to illuminate the object of interest. And so with that, there's actually there are pinouts right here. So this makes it so it's very easy to put onto a breadboard. And so what we have here is voltage in. So we're not going to use this one. This is the one. This pin is used if you want to power this on 5 volts. What we're instead going to do is you're going to power with the 3.3 volt line and the ground pin. Okay, and then there's, as you can see, the serial data line and the serial clock line that we need for I2C. And this is the LED if you want to actually turn the LED off. So by default, the LED gets turned on when you power it on 3.3 volts. This, if you connect to ground, will turn off the LED if you need to. There's this thing called INT. It stands for interrupt. It's to use the interrupt on the color sensor, but we're not going to be using that. That's more for an advanced application, which we might be discussing in a more advanced tutorial later on. But yeah, this is what we're going to be using ultimately to detect colors. All right, so we're going to go ahead and hook this up onto the breadboard. So I'm just going to go ahead and put the color sensor onto the breadboard itself. Just stick it in there. And then we're going to go ahead and connect 3.3 volts to the power line. And then later we're going to be using the microcontroller power wire and connecting it over here. So we're just going to go ahead and put connect this to the power line, 3.3 volts. I'm going to go ahead and connect the ground pin on this to the ground rail right here. All right, so that should just make it so it's a little more organized, so we can connect the 3.3 volt line on here to 3.3 volts on this little power rail right here. So locate the 3.3 volts, as always it's the fourth one down, so 1, 2, 3, 4. This connects to the power line. And then we're going to go ahead and locate ground, which is actually always right here, either one of these 2 pins, so either the second or the third from the bottom right here. So we go ahead and just connect that to the ground line right here. Okay, now we need to go ahead and locate the 2 pins that we're using. So it's going to be P2.1 and P2.0. And PTB1 is going to be used for our data line, and PTB0 is going to be used for our clock line. So PTB0 is actually right over here, which makes it actually pretty convenient for setting this thing up. So PTB0, and this is going to be connected to our clock line. So find SCL over here, which is right here. And then PTB1 is the one that's right below PTB0, and that's going to be connected to our data line. And that should pretty much set it up. Let me just go ahead and grab a USB and power this up. So if I power this up, what you're going to actually see, the LEDs are actually going to be very, very bright. So with that in mind, we're going to go ahead and just show you exactly how to turn it off if it really upsets your eyes. So if I connect it right here, it'll be this super bright light. Now, it's very, very bright here, but you actually can see on the camera screen, unfortunately, it doesn't actually show it with much detail of exactly how bright it is. It's very, very blinding to my eyes. But if you go ahead and connect the LED pin to ground, you can actually turn it off. There, like that. Okay, so this is pretty straightforward in terms of connections. Again, it's just the power line. You just connect the power line, 3.3 volt line, ground line, SDA, and SCL to the respective pins on the microcontroller, and this should be good enough. So we're going to go ahead and write some code up to interpret this. But before we do that, we should actually read the specification sheet, so we just know exactly what registers we want to actually program, and actually how to read out data from this chip in particular.